Good morning. Welcome back. I hope you've had a good last few days, and I just want to mention that coming up soon here after these next two lectures will be your next exam, Exam 2, so be sure you're ready and aware for that. The topic, as I mentioned in the last lecture, deals with water. And of course, this is a real pet type of topic of mine. I know that in classes past over many, many years, I've kind of made a statement like this, that if I'm walking along a street and I run into you 5 years, 10 years, 15 years from now, and I ask you a question about this topic and you don't get it right, I'm going to go back and change your grade. I'm just kidding, of course, but the reason I make a comment like that is that to me this is a really, really important topic. Water is an issue, or water is a thing that without it, we don't have anything. We don't have food. We don't have quality for a lot of things. And life would be really dramatically tough without water. And water's been an issue mainly from an environmental standpoint, from a standpoint of quality of water. So the next two lectures I'm going to spend talking about features about groundwater in particular, about some of the terminology we use to discuss groundwater. I'll also talk about water quality today, and I'll say a little bit about where the city of Hays, Kansas gets its water. And some of these issues, of course, I expect you to remember for the exam. Now, I always start this lecture out with this poem, or part of a poem, that you've probably heard periodically in your past. Water, water everywhere, and all the boards did shrink, etc., etc. And maybe or maybe not, you might remember from your literature classes who wrote this, and I won't quiz you on it right now. You just kind of remember about Coleridge, the rhyme of the ancient mariner, in this case. But this picture is actually a photograph of part of the Earth in the Pacific Ocean taken from space. And what you see down here in this zoom up are a whole bunch of little islands out there in this vast sea of water. As you recall, the last time we talked about where water comes from, the big blue planet, that most of the water on the Earth is salty, and we don't have a lot of other water to work at. So again, I want to kind of go back to some of those numbers a little bit before I get into the guts of this stuff today. Nice picture of an artesian well right here, kind of unique, kind of spouting out of the water. So this is groundwater part 1, and we'll do part 2 in the next lecture. So I do have a beginning outline of, well, if water is such a big issue for us, where are we going to get some more? Now I know, maybe, I hope, some of you have read the newspaper periodically. If you're from western Kansas and you've looked at this in your local newspapers or heard things on the radio, whether it's county level or city level or state level, whatever it is, water is certainly a very interesting topic in the newspaper. You can't go by a week, sometimes a day, without seeing an article about who's challenging who over water rights, things about water quality, and so on. So obviously, as the population grows, and maybe businesses change in the future, and as I mentioned with oil shale, if we need to have more water to process oil shale, where are we going to get it? Where could we get more water in the future of this planet? Well, I'm going to go through kind of a list of some of these things. Obviously, we have rivers, lakes, and swamps on the surface of the earth. But, we can't go at swamps anymore, at least in our country, because of what? The Wetlands Act. We passed this legislation that we can't drain swamps out because it's part of the ecosystem. That's the wetlands. Certainly, we have rivers and lakes around, so, in our past, we thought, let's divert, the Mississippi River, or part of it, into West Texas. We do that anyway, not into West Texas. We divert parts of the Colorado River into Southern California. There was a plan one time to divert the Yukon River through Canada, or part of it, redirect it and run it through Canada to the northern United, the plains. Well, Canada wasn't really excited about that at that time. There's been lots and lots of plans to do things with diverting water from rivers or lakes, and sometimes we do that and sometimes we don't, for a lot of reasons. But we still have that as a potential possibility. Now, groundwater Groundwater is where we get most municipalities use groundwater for their freshwater supply. Hayes does. Town of Russell, Kansas does not. They use the water right out of the river before they and then process it, of course, before they send it off to their consumers. So groundwater is a major issue. So why don't we just go ahead and start drilling more and more and more wells? Well, we could do that, but the issue could be, well, maybe you'll deplete the aquifer too soon. So a lot of things to think about. We'll come back to some of these issues periodically today when we talk about this in more detail. Recycle water. Lots of ways of recycling water in different industries that you can reuse that water. I know that over here on the campus of Fort Hays State, there's these ice machines. I've been told by the people who work over there that ice machines are notoriously bad for, most of the ice, the water melts. And rather than run it down the drain into the sewer system and move it on downstream, what they do with that water is they'll take and put it into a tank outside the Union. It's buried underground on the south side of the Union. It's a great big 20,000-gallon steel tank that was cleaned out. Air conditioners. They'll take that same air conditioning water, put it in there. What do they do with that water? They put it into the Fort Hays State's water line system to keep the grass green on the campus, in the inner campus. So that's just one little way of recycling water that we can do. Well, there's a lot of salty oceans, right? Let's desalinate the oceans. Well, we do. We have a lot of stuff left over called salt, though, that sometimes we have to pile up, and we know that concentrating salt at the surface of the earth isn't always good for certain vegetation, kills it. Whereas we might sell that salt to companies like Morton and so on that we can use in food additives and so on. But desalination is very, very expensive. Now, we may get to that point in the future that we'll have to do that, have lots and lots of, desalination plants. What about icebergs? You see these things in the news about the global warming and all the big chunks of fresh frozen water, big icebergs coming off of Antarctica and Greenland and wherever. Why don't we lasso those and melt them and use that? Well, that's been tried, by the way. In fact, it's coming back a little bit. In the Indian Ocean, back in the 60s and early 70s, I think Saudi Arabia actually went into the southern Indian Ocean with big boats and brought back large icebergs and then processed that water right offshore. And I don't have the number exact, but I think at that time it was about $1 a gallon for water. And they felt that was too expensive, so they didn't pursue it. The idea comes back, supply and demand. We'll see. I'll say something else about icebergs in just a bit. Now, we have new technology at our disposal maybe to try to find more water sources, and particularly groundwater sources in certain regions of the earth where we might be able to use infrared or radar to penetrate beneath the surface layers to see if we can find, deposits of rock material that would hold water underground. That's a possibility. I'll try to show you one or two pictures of that in this lecture. By the way, I want to go back to that picture. I don't know if this is the cold season. Every time I see this picture and I think of the cold, we have coughs and sore throats and stuff. It always reminded me of the Smith Brothers cough drop box, but that's not who that is. I'll come back to that individual later on. All right, now, this image from space are the Great Lakes that border the east central states of the United States and Canada. You can see Lake Michigan kind of in the middle in there. And Chicago down in that bottom left-hand corner. Of course, you know where Green Bay is if you're a Green Bay Packer fan. 20% of the world's fresh water is in those Great Lakes. 20% of the fresh water. So we have a good supply, fortunately, around us. That's nice. 90% of the U.S. fresh water, if we ever needed it. That means we got to what? Empty the lakes out, though. People living along the lakes and all the transportation of shipping and so on may not like that, the recreation stuff. 40 million people live along the margins of all those Great Lakes. And that population is growing. Now, Droughts come and go, weather conditions change, but the use has gone up, and for a variety of reasons that are a mixed bag of all those, from the drought, lesser rainfall, and so on, is that Lake Michigan alone, from some of the studies, have been dropping. It's down about 4.1 feet. That's a lot. Now, if you've got front, lakeshore property, your pier may not go all the way out to where it needs to sometimes. So it may not look as good. So that's going to change and fluctuate, but something to think about if we start taking more water out of there, what that might mean. There's that picture of that guy in the lower left-hand corner again. That's Sir Thomas Crapper. At least, now I don't mean it in a derogatory sense. This gentleman was a plumber for the King and Queen of England. And if you think back of water and issues about water back a long time ago, before we had sewer systems and water lines and toilets, it was a health thing. It was a health thing. And so here we have an individual who invents a device that's part of the cleanliness process of water issues and sewer lines and so on. And he invented the flush toilet. Now that brings me to the statement about, for a long, long time, at least in our country, in the United States, that the common, average, older toilet, you flush it, you use up 5 to 7 gallons per flush. Back in the 80s, when water was a major issue here in Hays, Kansas, in western Kansas, the city of Hays offered people who lived in town a reduced price, if not a free toilet sometimes. There would be a more modern toilet, 2 to 3 gallons per flush. They'd give you shower things and faucet things that would be low flow for free to help that process. So anyway, when you think about that, if you don't own your own home right now, say you live in a dormitory, your landlord pays for your water, my average water bill runs around $46 a month. I pay for the water that comes into my house and the water that leaves my house, the sewer line system. And that will fluctuate depending upon the time of the year and how much you use. Now, we're a family of 3. If you're a family of 4 or 5 or 6 or whatever, that's going to go up. You have to pay for that. And you start getting pretty water conscious in how you do the dishes, or how you flush the toilet how many times or whatever. You could start putting money down a drain, and no pun intended in there. But I put that comment up about Sir. I know that for a long time some claims that this individual was knighted by the King and Queen, became a Sir. The more recent research by historians saying that that's probably not true, that he wasn't really Sir Thomas Crapper, he was just a good old plumber, but certainly a good inventor that helped things. There's an individual up in Alaska, I think it's in Anchorage, who said, you know what, I think I could get my plane, fly out over the sea, and target some really neat looking icebergs. They're free. I didn't find any legislation about who owns the icebergs out in the ocean. They're fresh, frozen water. I'm going to take my GPS, target it, send my shipping crew out there to lasso it, bring it back to port, and I'm going to process the water and make that water bottles you see up there and sell it. It's expensive. I don't know what it costs per 6-pack, but I know it's not cheap compared to most bottled water, but it has this aura of being the most pure water from ancient times when we didn't have the industrial situation and herbicides and pesticides and so on. But it's coming back. You can buy glacial water these days. On the left's a picture of a regular photograph of part of the Sahara. Big old sand dunes. The black parts are rock outcrops, but the more reddish tan, or I guess reddish on the screen up here, is sand dune complexes. With remote sensing, you can't always see through that sand real well. Radar is very useful. Radar is very good, and lo and behold, in looking through that sand, those dune complexes, we can see old, coarse-grained river channels. On this right-hand side, these darker areas represent the old river channels. Well, that's coarser deposits. And those coarser deposits are a good place to drill and penetrate and put wells in, because that's where the water is going to accumulate. So we can kind of see through this. So remote sensing might provide a way to kind of speed things up for us. I know in the desert regions of the world that that's a really, really important issue, having water. And I could go on and on and on today about all the water situations on politics and so on. Countries that aren't really the best of friends are really friendly when it comes to water and how they're going to try to share that water. And sometimes we're not as friendly. I might mention, maybe sometimes about how Kansas was suing Colorado, and Kansas and Nebraska were fighting over water, and how Mexico was picking on the United States with the Colorado River. These are issues that are part of everyday life. Out here in the western part of Egypt, there's the old Siwa Oasis. Interesting place about, has a lot of historical significance. Cleopatra and stuff like that, and how these pure, clean spring waters were coming up out of the desert sands and had this oasis there. Well, the water pressures were going down a little bit, and so the engineer said, let's go out there and drill some new wells. Well, they did, but unfortunately, by drilling into the underground subterranean areas to get the water out from these springs, and pulling new water out in an area not too far away, affected the hydrostatic head system, the pressure systems in there, and now it seems to be worsening. And this is a major area, by the way. They use this water for growing dates. It's a major production for food in this part of Egypt, and so we'll see what happens in the future. Yeah, we can go after the water, but we better be sure we do it well. So these new wells have kind of altered the spring systems, and we'll just see how bad it is in the future. Now, we've kind of looked at this a little bit. I'm going to just give you some generic numbers, the red stuff a little bit, and I'm not going to make you memorize all these percentages per se, but again, about 70% is covered in water, the earth is, and of course 96% of that's salty, so we've got about 4% left. 3% of that 4% is frozen in glaciers and permafrost regions, so there's about 1% of fresh water on the planet that's available for all of us. All us plants and all us animals, so to speak. All right? And we're growing. And so we have a lot of needs. Something to think about. 1%. Probably the most important number out of this would be that last statement about 1% is available. About 1% of the fresh water on our planet is available to us right now. Now that can change, as we might want to go after that frozen water, or we want to desalinate this. That's that supply and demand and how drastic we get. Kansas, right in the middle of the map there, annual precipitation rates. Hays, Kansas is kind of what we classify as a semi-arid environment. We get about 22 inches of rain a year. You go to eastern Kansas, Manhattan and Lawrence, it jacks up higher. A little more humid in eastern Kansas. You get into western Kansas, out there by Tribune and Colby and Ulysses, much drier. And so that is going to be part of this process of how much water is going to go into our groundwater system. If it's hotter climate, how much will evaporate? So back to that water cycle diagram we had the last chapter. There's that term, evapotranspiration. I'm not going to go into the detail again about this diagram, but I will focus on one thing. The groundwater part of this water cycle. Hydrogeologists classify 3 types of groundwater. The list of 3 on the right-hand side are 3 types of groundwater, and I'm going to go through them right now. The first type of groundwater is referred to as meteoric water. It's the water that comes from precipitation, rain, snow, sleet, that hits the surface of the earth. Okay, meteorology, the weather. Meteoric water, where rain and snow hit the surface of the earth. Now some of it will evaporate, as I said, and some will run off, and some will get stored in lakes. But that part of that soaks into the ground That portion is referred to as the meteoric water. The source is from the sky. Now if you look at the diagram a little bit closer, you can kind of see a river meandering through just above the word runoff, like the Mississippi, and it goes out in the delta. We have water flowing into the lakes or into the oceans. If you've ever been down to a beach, you pick up some loose sand, especially not the dry stuff, but out there you have a lot of water seeping out. So out there in those loose sediments, in between all the grains is what? Water. And it's usually saltier types of water because it's mixing with seawater. If it's a lake, it can be fresher water. But in between all those grains, we're getting water that's trapped during deposition. Well, the second on the list is called connate water. Connate water is this trapped water, trapped during deposition. So all our continental shelves and those sediments down there have lots and lots of water trapped in them. Even if they get lithified into a rock, we can still have water trapped in those pore spaces. That's the connate water. And the last type, juvenile water, is really the water that's still coming out of the interior of the earth from the beginning of the formation of the earth. And it comes up through magma. We talk about wet magmas and dry magmas. Wet magmas have a vapor, a steam, water vapor associated with it. So any kind of moisture coming through magmatic and plutonic activity, that's referred to as juvenile water. But the number one water that gets involved with us, that moves through this cycle very, very, very rapidly, and we use most often, is meteoric water. There's a lot of weather, a lot of rain, a lot of snow, a lot of percolation of water into the ground. That's meteoric water. Now there's a lot of stuff on this slide, and I don't want you to write it all down. I want you to look at the top part, and we'll focus on that. Here's another term I had mentioned already before. Hydrology was a study of surface water. Hydrogeology is a study of groundwater. We're looking at the layers of material underground, the sand, the silt, the gravel, the rock layers, whatever, that contain that water and how that water moves around in that system and how we get it out. That's the study of hydrogeology. When we start thinking of this groundwater again, as I mentioned at the very beginning of class today, that groundwater is the largest source, or the main source that most people use. It's the largest source of economically available fresh water for us. And out of that water, most of it is used on this earth to grow food. Irrigation, about 80%. That's a ballpark number. And all the 20% left then, 20% is used for other stuff. Now everything on the bottom, you don't need to write that down. You can just kind of look at it. It's in the PDF file anyway, but what do we need? Here's where these priorities now come in and what we're going to decide what we'll do with the future of our life with water. Where do you create your priorities? Everything on the left you have to have. We need water for those things. Yes, they're tied together in some biological sense, from respiration to metabolism and photosynthesis and so on, but you have to have water for that. We don't have to survive as humans to have the water on the right. Some people think we do.